Alright guys, BuildZoid here, and today we're going to be taking a look at some, voltage regulation performance measurements that I took of two of my R9 Furies, which turned kind of into three R9 Furies, except, I mean, this is still the same card, it's just that now, like, you'll see the modifications I've done to it, but it is modified, so... Anyway, so I tested the XFX R9 Fury and the Sapphire Nitro Fury, and both of so the Nitro is a custom PCB from Sapphire. The XFX Fury just uses the reference AMD PCB. There's actually quite a few, like Gigabyte actually has a pretty interesting R9 Fury PCB, and then Asus especially, like their R9 Fury Strix. Like, first of all, there's two variants of that PCB. Both of them look really interesting. Like, I'd love to test either of them. Or both. Ideally, I'd test both of them. But, getting, like, the thing is, like, the Gigabyte one is probably the rarest card, and then the other two, like, there's no reliable way to tell if you have a, like... I'm not sure that there's an easy way to tell which Fury Strix PCB you're looking at if you're, like, just trying to find it on eBay or something. So, and also the Strix Fury doesn't really show up on eBay very frequently these days, so that kind of sucks. Because it is a card that I've been looking out for, because, yeah, I'd like to do measurements like this on one of those as well. But anyway, so I tested the Nitro Fury and the XFX Fury. So the XFX card, unfortunately, has an absolutely god-awful core, which I didn't realize before the start of testing, and then... Yeah, so we have a bunch of results here which are like the frequency ideally would have been the same. Like, I don't know why I decided, like, I thought 1100 megahertz wouldn't be an issue until I realized that XFX card needs way too much voltage for even 1100 megahertz, and then it's just like, well, then if the voltages are different, then the results don't count, and it's just like, okay. So, yeah, at the same time, a 2% frequency difference between the cards just isn't likely to make much of a difference to the actual measurements, but it's definitely not optimal for, like, measure. Like, you should control your variables, and that's not very well controlled right there. Other complaints I have for my own data, because nothing is ever good enough for me, right? So, my own data, like, well... The oscilloscope, like, all of the values here are plus 4 millivolts minus 5 millivolts, because that's the rounding. Like, the rounding kicks in. So, like, this could be 1.094, or it could be 1.085, right? Which is pretty annoying. So yeah, I wish the oscilloscope was had, was, I guess more sensitive would be the best way to describe it, I guess. But yeah, if I had more resolution, that would be great. But I don't. So, because the thing is like, well, oscilloscopes get very, very, very expensive. So, that's kind of that. Anyway, yeah, so there's the measurements. And, well, this is annoying because obviously if you're looking at something like this could actually be a difference. Like, the difference between these two values could be anywhere from, like, 1 millivolt to 20? Because this could be, like, 1.05. Yeah, it could be as much as 20 millivolts of difference at, like, between this measurement right here and that one. Or it could be just 1 millivolt, right? Because... this could be 1.094, and this could be 1.095, and then it gets rounded up to 1.1, which is, yeah, not great, but there's not really anything I can do about that. Anyway, like, the thing is, the results still make sense that the XFX card would actually beat the Nitro, which I was honestly hoping the Nitro would beat the XFX card, because it is a custom PCB, and Sapphire did put some, like, there are, like, they did make some upgrades to the PCB, which are rather nice. Like, they went from the direct FETs to some power stages, but the problem is that, like, it basically seems like Sapphire optimized their VRM design for thermal performance and, I guess, efficiency, and then the fact that, you can also... like, getting really good voltage regulation performance tends to be kind of expensive, so they were just like, nah, we're not bothering that. So... not bothering with that. So, yeah, the results here make sense when you look at the PCBs. So, the XFX card basically has massively less overshoot. Also, I tested at matched average voltage and also matched set voltage. This is another thing that honestly I could have dealt with better with the voltage readings, because the thing is, the average voltage, I think it's honestly getting pulled up by the overshoot more so than being an actual, um, well, like I should have had like I should have also hooked up DiSense or something. And so this is another issue, is just like and also the accuracy of the average voltage is again plus 4 millivolts minus 5 millivolts. So there's some rounding error in there as well. That's actually kind of significant. Um, but Yeah, so not super. So, I have some results where it's like I'm trying to match the load voltages, and then I have some results where I'm just kind of matching the set voltage. But even if we look, if we look at like matched average voltage, then the XFX card absolutely destroys the Nitro Fury, right? Like that's a 30 millivolt improvement in minimums. And there's still less overshoot. Whereas if I run it at matched set voltage, the minimums are margin of error, but it's still like wipes the floor with it on overshoot, right? Because that's 40 millivolts. That's well outside margin of error. And then if we look at other tests, like the other thing is it is consistently getting 10 millivolts across like a variety of workloads, better results than the Nitro Fury. So, yeah, it basically looks like the reference PCB is just better than the Nitro PCB, and when we look at it, it'll make sense why. So after doing this first round of testing, I was like, okay, well, that I find that very disappointing. I will not accept having the card with the nicer heatsink, um, and like the custom PCB having worse voltage regulation performance. So I went ahead and just did a Buildzoid edition where it's just like fix the problems, right? So and so this is matched like average voltage, and this is just matched set voltage. What's really interesting is that like the voltage is not entirely consistent across all tests, but again, like the scope rounds up across a 1 millivolt difference, right? So it's just like if the difference between these two voltages was really borderline, where you could actually consider them the same thing, well, the scope's actually going to make that look like a 10 millivolt difference because of the stupid, like the fact that it's rounding up or down depending on where exactly your last millivolt ends up. And so that's really, really annoying. But yeah, so matched set voltage, I've managed to maybe pick up 10 millivolts on the minimums. But then if we look at like TimeSpy GT1 and GT2, I am just absolutely destroying the stock version of the Nitro. So I'd say that actually worked. And even GT2 Firestrike, is a win. So I'd say this, like, I'm not entirely, like, again, basically there are some things I'd like to adjust about the testing methodology. That would be like having a scope with more resolution. Then also I did notice some weird problems going on with the actual way I had the oscilloscope connected when I was testing the BZ the built like the modified Nitro, where basically what I ran into was like I think the probe basically slipped out a little bit out of like the connector that I have for it, and basically was suddenly getting the same peak to peak values as the like stock Nitro. So there's maybe a chance that this wasn't properly hooked up to the oscilloscope, and that's where some of the extra like that is like possibly a source of error. But like now I don't have another stock Nitro to validate that, so that's kind of like, well, too late. I can't actually check if that is the case, because I didn't realize that would be an issue until I was testing the BZE, and while testing I nudged the table the test system was on, and suddenly the measurements were just off by like 50 millivolts, and I was like, how did it just go up like 30 millivolts and on the peak to peak values? And then I after fiddling around with the probe a bit, it suddenly went back to normal, and I'm like, oh, okay, well, like sucks to be me. Like sucks to be me because it's just like so there's like this data so like we already like I already have problems with the fact that the scope just doesn't have enough resolution, and then it's like there's a small chance that all of this right here is just completely wrong because maybe the probe wasn't hooked up quite right. um and yeah, there's not really too much I can do about that at this point because I just don't have another Nitro, and I'm not reversing what I did to the one I do have. So it's just like, yep, that's kind of that the results are maybe very invalid. Now, what did I want to talk about? So yeah, so the results basically. It kind of looks like I did manage to get my version of the Nitro up to the same performance levels as the XFX card. At the same time, the testing methodology is not quite perfect, and I probably should have done some like max frequency stability tests. But the thing is that also is kind of unreliable because like Furies are very temperature sensitive. So like a small alteration in like room temperature, or well, yeah, like mainly like if the room temperature goes up 2 degrees, then it's like, oh, now it's not passing a test that it should be passing, and it's just like, so yeah, that is a really just annoying like doing this like yeah, just this stuff is really annoying to test, essentially, is what I'm getting at. Either way, well, I don't know. So, because I mentioned the attachment concerns, like if we assume that this was actually hooked up correctly, then I've made a significant improvement with the Buildzoid version of the Nitro. If we assume that this wasn't hooked up correctly, I might have not made a difference at all. That's basically what it comes down to. But the thing is, with the way the Nitro is designed, these results kind of make sense. So let's take a look at the actual PCBs. And no, we do not want to start with that card. Oh boy, I should have... Okay, wait, give me a second. And this is... I forgot to like undo everything after one of the takes. Okay, this is where I want it to be stopped. Okay, so I close down the layers, and somebody's going to be like, you should edit, and it's just like, well, screw you. Anyway, so here we have scope shot, pictures from the oscilloscope, and so this is Firestrike Graphics Test 1 running on the XFX Fury, and this is TimeSpy Graphics Test 2 also on the XFX Fury. This is basically just to give you an idea of what the oscilloscope is looking at. And so what's kind of neat here is you can actually tell, like you can measure, you can tell the frame rate at which Firestrike is running from this right here, because basically if you go from here to here, I'm not sure that corresponds with the start of a frame render, but it like the repeating points, like you can go from there to there, or you can go from here to here, or from here to here, right? Like any point that is like any spike that is repetitive and regular, you can actually use it to, like, if you measure the distance between them, you can get the time in milliseconds between the spikes, and you can calculate the frame rate from that, which is kind of neat. So like I think these two are like what is that? That's like 1 division, 2 divisions and a half. That's like 2.5 divisions, so that's like 12.5 milliseconds right there. So that's like 80 FPS, I think, maybe. Don't like, I'm trying to do that in my head, which is a bad idea, but yeah, that might be like 80 FPS, because that sounds right, because 60 FPS is 16.66 milliseconds, so 12.5 should be 80. So anyway, so that's kind of neat, as you can see the frame rate on there. Then I really wish I knew what like the different spikes in this correlated to in terms of what the GPU is currently doing, but unfortunately I have no idea. So it's basically like what we're looking at is the basically we're seeing the consequences of the GPU's core pulling varying amounts of current and how the VRM deals with that. So that's why it's called transient response. Is just like the transient in current and how the VRM responds to it. And the funny thing is, one of the easiest ways to get a good transient response is you just throw a bunch of capacitors at the problem. It's generally the best way to try deal with it. Except for the part where it eventually gets really expensive and just complicated, like just fitting the capacitors onto the PCB starts being an issue at some point. But anyway, so that's that. And then GT2 Time Spy runs at a much lower frame rate. I think this is actually from the start of the test, which is especially slow in terms of how many frames it runs at. And so you can see that like we don't even have like 2 full frames here, because we have like from here to here is like 1 frame, I think. Yeah. So like there to there, that would be like 1 frame. Well, that'll give you the frame rate right there. I'm not sure that that's an entire frame again, but you can sort of see the repetition of like this part and this part. Anyway, so I just wanted to sort of show you what it looks like when a GPU is running. It looks very similar to like when a CPU is running, well, not super similar, but it looks somewhat similar to like a CPU running 128K FFT Prime 95, like an Intel CPU, because the funny thing is CPUs, because of how they work, are like, so here's a sort of neat thing is like if the GPU, so I could actually see the instability of the GPU core on the oscilloscope, because sometimes one of these, you know, basically blocks of noise indicating a frame rendering would just not appear. You would just get a straight line for that part, and that would indicate a frame dropped, where it would just error out and drop the entire frame, and it wouldn't complete the like it wouldn't calculate it. So that's kind of neat. You won't notice like CPU instability in the same way, because when CPUs run so much faster, and not, you know, periodic workloads where it's like, okay, we're going to get 60, like the workloads on CPUs aren't periodic where you just suddenly get like, now we're doing this, and then we're doing that, and then we're doing this, and then we finish the frame and we send it off, and then we do another frame, and you go through the same set of steps again. CPUs run much faster, so you don't really get something that looks a lot like this, unless you have a workload that is very steppy. But if you have a workload that's like Cinebench or something, it's just a flat line with the occasional spike from like the Windows event timer. So yeah, that's kind of an interesting difference between CPUs and GPUs. And then if you have a CPU that's running a workload that's very memory intensive, and the CPU is constantly like stalling out and waiting for memory access, you just get something like, you just get a mess, a very disorganized mess, because the CPU doesn't really have like, oh, now we need to wait for this much data for this period of time, because again, it's not very like CPUs work on much smaller chunks of work at a time, whereas GPUs compute a ton of data at the same time. So you get something that's very sort of periodic in that sense, which is kind of neat. Because on a CPU, like here, you can actually see the frame rate. On a CPU, you just kind of don't really see anything. Anyway, so that's the scope shots. Here's how the oscilloscope was hooked up. Right, so this is the Nitro. Oops. So here we have the Nitro, and for both cards, I was measuring from this capacitor right here. So this is the XFX card. You can see that that is the same capacitor, because we have these two over here, and then we are on this one, and on the, you know, two over here, and we're on this one. So that's how I was measuring. The wires are like, the thing is, I could go for a shorter attachment method. The problem with a shorter attachment method is that there's a good chance that the probe hanging off of the card will damage the multilayer ceramic capacitor, and I don't really want to break the capacitor. There's not really like dedicated convenient probe points that I could use on the card. So yeah, these little extension wires are pretty much they're a convenience thing in a way, but it's just like, I don't really want to run the risk of breaking a capacitor. It's not fun to deal with. So yeah, the obvious downside is the longer the longer the wires you have, the more susceptible they are from just picking up the more susceptible they are to picking up noise from the environment. So that's kind of the main concern with this, but I'm using the same exact set of wires on both cards in the exact same location. Both cards have backplates. So, you know, we shouldn't really be, and we're nowhere near the actual, like, if you're on a motherboard and you try to put a oscilloscope probe anywhere near the inductors, you're going to pick up inductor switching noise, which is just like, you don't really want that. in your measurement. On the other hand, with a GPU, the inductors are on the other side of the PCB. And so between the inductors and the probe, there's a great big ground plane. And also then there's the backplate on these cards. So it's just like, it's not really much of a concern. Because the thing is, when I do CPU measurements, you can actually see the VRM switching noise if you look for it. But with the GPUs, like, I can't find it. So, which is just a benefit of how GPUs are laid out, like where you measure from on a GPU. If you measure from the back of a motherboard, it's also not really a concern to pick up like VRM switching noise. But the problem with measuring on the back of a motherboard is that you're measuring from behind the CPU socket, and the socket is this great big awful resistor, so your measurement is just completely way off in terms of voltages. And this also is a bit off in terms of voltages because obviously I had a set voltage of 1.2 volts, and on the back of the core we're measuring like 1.21 volts, which is it's a bit too high. It shouldn't be measuring that high, but that's just that's just a consequence of the fact that I'm using a passive probe instead of an active probe. So, and there is a workaround for that, but I figured that out way too late into the test data. So I was just like, well, we're just gonna have to use the results that are measuring a little bit too high, like because the thing is, like, I actually like the workaround. I checked that ultimately it doesn't change the relationship between the average voltage and the minimum voltage. It just lowers everything by like 10, 20 millivolts. So consistently, like it just brings all of the measurements down into what would be an actual accurate voltage measurement, but it's just like I have a bunch of data that is measuring, with one method, and then it's like, well, if I measure with a different method, then it's like, well, now it's not comparable at all. So yeah, I hate this kind of testing. I absolutely hate it because it's like every time I feel like I figured out some nice, easy, convenient way of doing things, I find out that actually, no, you haven't. You like tweet like, the probe gets nudged and suddenly the measurement is off, or you notice suddenly like, oh wait, now it's measuring less noise than before, and it's just like, oh no, it's not hooked up properly, and then it's things like, oh, it's not like the issue is like the thing is like the scope and the system are on the same ground, like they're both connected to earth mains and they're on the same power strip, but the problem is there's still a voltage difference between them, and it's not very big, but it's enough that without a workaround that I came up with, it skews voltage measurements upwards. So yeah, that's another issue, is just like that's why basically behind the core, where really like behind the core you should be getting almost exactly the same voltage as if you were measuring dye-sense. I'm measuring like 20 millivolts off, and it's just like, well, it's because of the fact that I'm using a passive probe, and I didn't like try like the thing is like I can't float the system because I've tried that and it just really doesn't work at all. But yeah, and I can't float the oscilloscope. Like, I've tried both of those, and it's just like floating either of them causes massive issues. The only active probe I have is really low bandwidth and kind of noisy, so it's like we can't, like, I don't really want to use it because it's like the resolution problems of my oscilloscope with the active probe are even worse. And so it's just like, well, we have measurements that unfortunately are off in the sort of voltage. Like, the voltage is off by some amount, but it's consistent, so I'm like, fine. Hooray for like nice active probes are extremely expensive, especially if you want like an active probe specifically designed for doing like power supply noise measurements like this. They go well over $1,000, and then they don't even like. And the worst part is those kinds of probes don't even hook up to the cheap oscilloscope. So then you need an expensive oscilloscope for your extremely expensive probes, and it's just like, yeah, how about no? Or more like, well, it's actually, it would be yes if it weren't for the part where I'd have to pay for it, right? Like, that's the main issue. Anyway, so let's take a look at so this is the XFX Fury. Right, you can tell from the warranty void if removed stickers, which I'm surprised this card still has those. But the thing is, I really don't like disassembling Furies because the interposer scares me a lot. Like, you touch the interposer wrong, and it literally is just a matter of like you touch the interposer wrong with an object that's slightly too hard, and no more GPU for you. You're going to kill it like that. And it's just like, yeah, how about just no, I'm not going to take cards apart unless I absolutely have to. So anyway, so basically the VCore power filtering that we're looking at here is all of this. And the cool thing about the reference Fury PCB, at least for my convenience, is that basically all of the capacitors are on the back of the card. Actually, not even basically. Literally all of them, unless you want to count the ones that are like here on the substrate. But those are the same for... And I'm actually not sure that all of these are VCore, but a lot of these will be VCore. Like the little capacitors around the core. A lot of that will be VCore. Some of them will be for things like PCIe as well as memory and memory controller, HBM. You get the idea, but a lot of them are often VCore. So we're not really interested in that. Let's go back. So the main, like the thing that the actual PCB of the GPU affects is like this configuration right here. And so on these cards, you basically have this. And now I'm not sure about this row of capacitors right here, if they're VCore or maybe they're HBM. Not sure. Haven't checked. I don't have schematics for GPUs, unfortunately, and there's not really much I can do about that. But yeah, at least this much is definitely VCore. And so you just have this huge capacitor configuration here. And the thing is, this, from like this line onwards, everything is standardized. Like every single Fury has this set of capacitors right here. Well, actually, it's like this set of, well, yeah, this entire area is basically the same on every single Fury, or more like there. Like there's basically a square area around the GPU core where it's standard, like that's just AMD says you do it this way, and that's the way you do it because AMD says you do it that way. So basically when the various GPU manufacturers want to mess around with the power delivery filtering, they get to play with it in sort of everything that, you know, sort of to the... where is that, left of this line right here. Yeah, here you can do whatever the hell you want, but on the right of that line you need to follow the AMD guidelines up until around this point. So, you know, so this is all standardized as well, or the same as well. But anyway, so on the XFX or the reference PCB, we've got all of these 560 microfarad aluminum SMD aluminum polymers, and these are the really good type of SMD aluminum polymers because these are the 3-terminal variant. So basically, you've got a tab right down the middle that looks kind of like this, and then you've got a tab over here. This side goes to VCore. And then you've also got one tab over there, and that's your, you know, you've got your 2 ground tabs. You've got your voltage tab over there. And these are cool because this 3-terminal package, so the 3-terminal package exists because it drops the ESL of these capacitors even lower. And they're already much lower ESL than your regular through-hole capacitor if you have the regular, like, 2-terminal variant. But if you want to spend extra money, you can get the 3-terminal variant, and the ESL just comes down a bit more. And it basically means the capacitors are even better at filtering out high-frequency switching noise. Basically, when the GPU core suddenly wants a lot of current really, really quickly, the capacitor is much more able to provide that current than if it had a much higher equivalent series inductance. So, yeah, this is a really cool type of capacitor for basically, you know, filtering any kind of high... like power supply for anything high frequency, like say a GPU core, that also pulls ridiculous amounts of current. So these are really cool. Also, they come in really low ESRs. The downsides to these, they're extremely expensive, anywhere to like 4 to... I'm not sure on the specifics, but like getting specific price points from hardware manufacturers is basically impossible. They don't really share them with anyone. But like figures I was told was like anywhere from 4 to like 6 times more expensive than the equivalent through-hole capacitor. And that's as in the same capacitance. So, yeah, like these are very, very expensive. And actually, I think the numbers I was given was for 2-terminal polymers, not 3-terminal. So these might be even more than that. So that's one downside to these, very expensive. The other downside is you can't really get them in endurance ratings above 2,000 hours at 105 degrees. So You can't really like, we see a lot of motherboards and GPUs advertising like 10,000 hour rated capacitors. Well, they don't make these in 10,000 hour ratings because quite frankly the 10,000 hour temperature rating is kind of silly, like unless you're doing like server hard, well, it depends on your application, but for like gamers, very silly because if you have an 8 core CPU, you're probably never going to use more than 4 to the full, like you're never really going to max out the power consumption of it. But and so the VRM's never going to get that hot. So the high temperature, high, lifetime rating is just like, it doesn't really matter that much. Anyway, so lower endurance, but much electrically superior. That's the cool thing about these. And then we also get the multi-layer ceramics over here, and the multi-layer ceramics are just basically more of the same as these, except these come in even lower capacitances and relative to how big they are. So those get expensive as well, because you need a ton of multi-layer ceramics to get even close to like 560 microfarads, right? Like the largest capacitance you can get in this package size that I'm aware of is 47 microfarads, assuming that you're not buying them in some really low temperature rating, which again you wouldn't use because this needs to be near the VRM, and VRMs tend to run a bit hot. So yeah, you like generally these capacitors you'd want them in like 105, maybe 8. Like at lowest you'd want an 85 degree rating. I normally buy mine at like 105 degrees. And then a lot of the time you'll see like the capacitors right by the actual MOSFETs. Those will be like 125 degree temperature rating. So yeah, anyway, that's the output filter here. So we've got the really expensive 3-terminal aluminum polymers and then a bunch of multi-layer ceramics. So very low ESL, very low ESR, however, pretty damn expensive. And relatively low capacitance, because these I checked, these are 15 microfarads each, or so these are 15 microfarads each, but we're not going to count them. So yeah, and these 560s, well, these are just 560, and there's 12 of them. Now, if we look at what Sapphire did for their Nitro, you'll notice that, yeah, they've got the standard part from AMD here. That's still the same. That's the same on all of the cards. But the multi-layer ceramics that are on the reference AMD card sort of in this area, well, they're all missing. And the SMD aluminum polymers, they're gone too. Instead, Sapphire just has a bunch of through-hole aluminum polymers in the 5,000 hour rating. So, higher endurance in terms of how long they can last at 105 degrees. These are from APAC. They're also 820 microfarads, and there's also 12 of them. So this has significantly more total capacitance in it, right? Because these are 820 microfarads, and there's 12 of them. Whereas on the reference PCB, you're looking at 560 microfarad caps. So, let's round that up to 600 times 12. That's 7,200 microfarads with rounding up. This, if we go 800 times 12, well, 8 times 12 that's like 96. So this is like 9,600 microfarads. So this has a pretty major capacitance advantage over the Sapphire card. I mean, over the XFX card and the reference PCB. But the thing is, these are through-hole aluminum polymers, so these have much more ESL, and Sapphire basically scrapped. So all of the multi-layer ceramics between the bulk capacitor bank on the reference PCB and the core, those are all gone. The actual SMD aluminum polymers, they're gone too. So Sapphire went with a cheaper capacitor bank, but much higher ESL. Because the other thing is, like, you can kind of try work around the higher ESL of your through-hole. Well, these could also end up with higher ESR, but you can get like a 5 milliohm ESR through-hole capacitor just fine. And admittedly, you can get like 3 milliohm ESR 3-terminal SMD polymers, but those aren't very popular because those are extremely expensive. But the thing is, like, yeah, so you can kind of work around, say, the, higher ESR and the higher ESL by just putting more capacitors in parallel, but Sapphire hasn't even done that. There's still 12 of these, right? So you have the same total number of capacitors, but these are just higher capacitance, higher ESR, higher ESL, maybe higher ESR. So basically, Sapphire's capacitor bank is cheaper and slower. That's kind of the main thing, is in terms of handling high frequency sort of switching noise from, say, from like the GPU core, this is just worse. So that would explain the results that we're seeing, and it's actually really interesting that this is so much worse on the overshoe, because that is one place where you'd actually expect the extra capacitance to help a lot, but I guess the GPU just transitions from like full load to idle so sharply that the ESL of these is just significantly hurting even that, which is just like, okay, so yeah, that's why you'd actually expect, like, SMD aluminum polymers are pretty overpowered. It's just like, if you get one good transient response, you just throw on a bunch of aluminum SMD polymers and everything's good. And if you want bad transient response, you go with through-hole caps. Um, the downside, of course, is like the other capacitors, you're paying 4 times as much for like slightly, like potentially even less capacitance overall. So, there's a balance that needs to be struck with the design, and that's also part of the reason why, if you look at the really ridiculous high-end, really ridiculous extreme overclocking cards, you see the capacitor banks where you've got your through holes for like the total bulk capacitance to be really high, and then you've got your SMD polymers, and then you've got just multi-layer ceramics wherever there was free space. So yeah, anyway, so I decided to obviously fix this, and this is how I fixed it. So we got some power bridges going on. This is just an experiment with, well, actually, it's not really an experiment. This was more like, how difficult is this to do? This is actually something you might see on like server PCBs occasionally, and some OEM PCBs as well. So like Dell, HP, Lenovo will sometimes have VRMs where you'll see basically solder strips going between the VR, like across the power plane. And the reason why this is done is basically, one, the solder mask actually acts as a thermal insulator, compared to, say, just bare metal like tin here. You can basically lower the temperature of the power plane, which the power plane is connected to the VRM, so you can lower the temperature of the VRM indirectly. This will act as a bit of a heatsink for that. The other thing that this does is it increases the cross-section of the power plane, so you get more current handling capability. Now, you can't really do this on most GPUs because most GPUs use GDDR memory, and GDDR memory tends to live right in this area, right? Like all around the GPU core, you have GDDR memory chips, and then you've got the memory traces running from the core to the memory chips. So you can't just scrape up the solder mask to reveal the power plane because there is no power plane on that layer. Now, with this card, I could actually go ahead and experiment with this a bit, and honestly, this is super tedious to do, and I don't recommend it. But it looks kind of cool. Really messy as well, but, well, I'll never probably implement this again. I'll just go with wires. Wires work fine. So yeah, we have that. And then, of course, the thing that actually, this, probably helped a little bit with the voltage regulation, but the main star of the show is the just capacitors absolutely bloody everywhere. So the big ones, these are 47 microfarads each. These are 22 microfarads each, and then these little ones over here, those are two, so like one of these is 4.7 microfarads, and that's a 0402 capacitor. So yeah, and I just went absolutely to town on it. The only cap behind the core that didn't get any extra capacitors is the one that the, probe hookup goes to, because the thing is, if I attach a capacitor directly to where the probe hooks up, it's obviously going to make the measurements different. So it's like, no, we will not skew I will not add any capacitance to where I'm measuring from. I will only add capacitance around it, which already that'll start skewing it as well, but it shouldn't be as bad. Like if we were literally attaching to an extra capacitor, I think like the impact it would have would be exaggerated, and I didn't really want to do that. So for measurement's sake, I did it this way. I guess another way to avoid this would be to use like dye sense voltage readings, which would also be an option. But yeah, those are a massive pain to get because the voltage controller is on the front of the card, and like I don't really like getting the wires running through the heatsink and all of that is just like, I didn't want to deal with that. So yeah, that's how this was hooked up. And I really did just keep adding capacitors until I basically started running out, like literally running out. It wasn't even like until I got bored. It was like, I literally don't have any more of these. They're all on this, like the remainder of my, of these that I had, they're all on this card now. Then for the 22 microfarad ones, I still have plenty of those, but I was like, I'm not going to have any, like, if I kept adding more, I wouldn't have any left for any of my other cards. And I kind of regret putting a bunch of them in this area, because honestly, like, you want your capacitors as close to the core as possible. So while this does look kind of neat, well, you know, it looks kind of neat in my opinion, but it's just like, this is definitely not the optimal way to implement these. I should have just stacked them over here, you know, just added them right there alongside those. One other thing I was considering was actually doing like a wire that would go like go from the sort of like solder bridge going here, then transition to a wire and then run the wire along a bunch of the capacitors and then potentially all the way to the core, which is an option. Like I can still do that. And maybe in the future, if I'm bored again, I'll do that. You know, just hook up some more power bridges to the card. Also, I probably should have put one here, like one of the scraped up solder mask bridges over here, because now it looks kind of like we have one there, we have one there, we have one there, we have one here, and then it's like, where's this one? Doesn't, like, not very pleasing to look at in my opinion. That one's missing. Yeah. So anyway, this is how I got the Nitro to actually like perform better. And the performance improvement, you know, we're looking anywhere from, well, okay, so at the same set voltage, it looks like it might have picked up 10 millivolts. This could also be a rounding thing. And actually, like, yeah, it could be a rounding thing, because if I raise the voltage by 10 millivolts, 12 millivolts, the result improve, like the minimum improves by 20 millivolts, which is like, that doesn't, like, that seems to be like something going on with the rounding there. At the same time, Firestrike GT2 for some reason didn't change at all, which is just like, okay, well, I'm not sure what's going on there. And the same is actually true for GT1 and GT2. So GT1 is for Times by GT1 and GT2. Like those didn't change, but those are significantly improved over the stock card. So those are like, okay, those seem to, like, I guess the thing with those is like they both run at lower frame rates. So maybe that has some, like, maybe that's why the extra capacitors are more effective in those. Or maybe it's just the nature of the frame. Actually, it could be more related to the fact, like, not that there's less frames in total, but that each frame takes longer to render. Maybe the ramp up and ramp down between the different, like, parts of the rendering sequence is less aggressive, which would make the capacitors more effective. Maybe. I'm not sure. I'm just, like, that's my best theory for that. So... yeah, and then the peak, like the overshoot is just way down. Like I've absolutely knocked that down by, well, actually for these two, for some reason it's down only 10 millivolts, but then like Firestrike GT1 is down 20, Firestrike GT2 is down 20 as well, or 10 and 30, which, again, like the thing is the scope rounding, you know, like on a, like, plus 4 millivolts, minus 5 millivolts, and that's when the rounding kicks in, and it's just like, well, that's really screwing with the results here, isn't it? But there's definitely, like, so it's hard to say exactly how much of an improvement I made because of the rounding screwing with everything, but I did make an improvement. I'm just not entirely sure how big it is. Now, the minimums do seem to be up a decent amount, so I'd say probably like 10-20 megahertz more core clock capability in the card. And so, you know, that basically explains why Sapphire opted for a more cost-effective capacitor configuration, right? Like this is definitely cheaper than what you have on the reference card. And well, in terms of the actual impact it seems to have on voltage regulation, it's about 10 millivolts on your 10-20 millivolts on the minimums. And in that case, it's just like, well, nobody's actually going to notice, right? At stock clocks, doesn't matter. It's not going to affect stock setting stability, like stock stability. So literally having a better capacitor configuration for the ability, like for Sapphire's ability to sell the card at whatever the stock frequency is, it has no impact, right? You could probably actually cut a bunch of these off and it would probably still run just fine. So, you know, that's one thing, is just like, like a lot, like the thing is basically going with a really ridiculous capacitor configuration for a GPU. Like, it's not a thing that you regularly see done on GPUs because it costs, like, it gets very expensive depending on how far you decide to take it. and the the benefits from it are very minor unless you're pushing like, you know, massive overclocks. And or well, it's not even about massive overclocks. It's basically like if you had a card that on an inferior, if you have a core, right, that on an inferior PCB does 2180, or well, that does say 1100 megahertz, then on a superior PCB with with a better capacitor configuration, because it's not just more, though in a lot of ways more does like the thing is, the more capacitors you put in parallel, the lower your ESR is. So it's just kind of like, in a lot of ways, more a lot of the time just works. You know, if you have the choice between a single 22 microfarad cap and two 10 microfarad caps, unless you absolutely need well, okay, no, that's not a great example. But if you had like the choice between one 100 microfarad cap and 10 microfarad caps, it's a very simple choice. 10 microfarad caps are better. Okay, like unless they're exceptionally terrible, they're probably like, you're gonna get a better result with 10 microfarad caps than with one 100 microfarad cap, because your ESR, like if the 10 microfarad caps are like 10 milliohms ESR, then their effective ESR when they're all hooked up in parallel is going to be like 1 milliohm. Whereas your 100 microfarad cap, even a good one, will be like, if it's a through-hole capacitor and it's a good one, it'll be like 5 milliohms ESR. So that's 5 times more ESR than the 10 microfarad caps in parallel. So in a lot of situations, just more caps, as in just sheer quantity, can end up being just better. But at the same time, it's just like that can get very expensive, because obviously it's also just like, eventually you start running into concerns like, well, how much time does it spend on the pick and place machine, right? Like it's potentially going to slow down. Like if you have a card with, you know, a couple hundred more capacitors than everything else, that's potentially going to start slowing down the production line whenever you're trying to produce those. Which that's one reason to not just whack on, like that's the main reason why you wouldn't replace because you could theoretically replace all of the through-hole capacitors with just this multi-layer ceramics, but you won't actually do that, because it would just take forever to be, like it would just start taking up tons and tons of time to assemble a card like that. Also, it would potentially take up a lot of PCB space, which is another like potential concern, where it's just like, where do you even put all of them? But yeah, the main reason why you won't see a lot of cards go for really like it's actually really strange how AMD reference cards tend to come out with, you know, capacitor configurations like this, because it's really expensive, and as we can see, like not necessary for running stocks, you know, running at stock. So yeah, that's the reason why most cards will generally, and actually even NVIDIA reference cards these days do it as well. Or actually, well, lots of NVIDIA reference cards do it, where they have a bunch of SMD capacitors and multi-layer ceramics and a really rather like impressive configuration of capacitors on the output. And the first thing the board partners do is just get rid of all of that and replace them with a bunch of through holes, and then it's like good enough right there. So yeah. But it's like I'm really sort of just find it interesting to actually get a measurement on these results. At the same time, I'd really like to test some like the Strix cards, because Asus actually, on the Strix card, you've got your through holes, and then you've got a bunch of SMDs as well. And actually, they don't even use like regular through hole caps. They use SMD through hole. Well, they use this like can style of capacitor with an SMD mounting end. So they're no longer through hole. But the thing is, as far as I know, the ESL problem with the high ESL of these comes from the actual packaging style. So the fact that they're a cylinder, not from the legs themselves. So even if you well, essentially what the surface mount variant of these does is it takes the legs and flattens them out. So it's just like, they're still there, they're just stubbier legs. So it's just like, yeah, no, that's probably, that won't really make a difference. But they do actually have a bunch of SMD, like, you know, this style of capacitor. I mean, this style of capacitor on the Strix cards. So I'd like to test those, because I actually, like, those are the only Furies. Well, also the Gigabyte Fury has a kind of interesting looking capacitor configuration, where it's like, that actually looks like it might match or outperform the reference cards. Whereas, yeah, the Sapphire just went for the sort of like it's not bad. It's not massively worse. It's just like it's not better, right? And I was kind of hoping it would be since it is a custom card. But obviously like Sapphire isn't a company that focuses on extreme overclocking. And so it's just like having a PCB where, because the thing is, you can also just bin your way to having a better average overclock on your cards, right? Like if you just bin the GPU cores better, that's going to make more of a difference than the capacitor configuration in a lot of scenarios. So, yeah. Um, but anyway, I found this like I plan to do this for a lot of my HD 7970s. So at the very least, like doing this testing so far has revealed that you know, I have some optimizations to make to my test methodology. I'm not sure if I'll bother testing like multiple different tests. I'm definitely dropping from the 1,000 sample size because at around like after around 500 samples, it just doesn't make a difference anymore. So 1,000 samples is unnecessary, but I'm not sure. Like, I kind of want to drop one of the graphics tests, or maybe throw in a different GPU workload. Maybe Unigine Heaven. No, Unigine Heaven's 4 minutes. I'm not like because the thing is like I actually run these on loop because depending on where exactly you start in say Firestrike or TimeSpy, like where you start recording. That'll initially skew the results a bit because there are some parts in Firestrike that cause slightly higher transients than other parts. But like if you just loop through it, like if Firestrike runs like 5 times in a row, then it doesn't really matter that much where you got your first 10 results from, right? Because it just averages out to something pretty representative of the overall thing. Um, which is why I test the way I do and have 1,000 samples. But I think I can cut down the sample size for the future because I do want to do this with like I have a lot of 7970s, so I have like a 7970 VaporX 3 gig, which is a different PCB from a 7970 VaporX 6 gig. I have a modified VaporX 6 gig. I have a 7970 Matrix. I want to get my hands on a 7970 Lightning. You get the idea. Basically, I'm gonna be like, this is testing that really like I find it really interesting to see these results. So I want to do more of this testing because, yeah, like, yeah, this is just kind of stuff that interests me, and because, well, yeah. Anyway, this video, yeah, so it's 50 minutes again. Oh well. Um, Even though like we are looking at like 10-20 millivolt. Like, because the thing is, like, yeah, if you look at the max voltage, it looks pretty, like, major differences. But the overshoot is, like, this is potentially concerning for the longevity of the silicon, but not really. Whereas the minimums, this is what actually affects your overclocking. But most of the time, the minimums, like, there have been, like, there's one motherboard I tested where the minimums on it are absolutely horrific. And it's so bad that it's actually noticeable, like, major disadvantage in terms of overclocking capabilities. But a lot of the time, with motherboards and GPUs, you're looking at differences of 10, 20, 30 millivolts. And when you're looking at differences of 10, 20, 30 millivolts, well, on a GPU, that's like 30 megahertz more core clock. Like there's very few GPUs out there that scale, um, like, yeah, like you don't really see scaling where it's like you raise voltage by which is really arbitrary if you think about it. Like the fact that this relationship kind of exists is weird to consider. But actually, no, if you looked at the voltages as percentages and the frequency as percentages, then it actually makes way more sense. But basically, if you raise the voltage by like 20 megahertz on 20 millivolts on a lot of GPUs, you'll end up with assuming that they actually scale with voltage, which there's plenty of architectures that just don't, but you'll end up with like a 20 megahertz increase in frequency for a 20 millivolt increase in voltage. And that's the kind of difference that having 20 millivolts more minimum voltage is going to make, right? So that's kind of the thing with this is just a lot of the time the test results are kind of like, well, there's not actually that much of a difference, but basically I think I've probably bumped the Nitro from doing like, I think the card already did like 1150 in its stock configuration. So now at the same voltage, it might do 1170. I really wish I had like, I should document what every single piece of hardware I have does in terms of frequencies. So then when I do these kinds of experiments, I can actually track like frequency improvements instead. The problem though with doing that though is that like a small, like especially with something like a Fury, these things are extremely temperature sensitive. Like 2 degrees temperature difference can easily make the difference between finishing a benchmark and not. Which is just like, well, if you're trying to do like stability improvement comparisons, yeah, that really throws a like that really throws that off, because it's just like, well, you need very accurate temperature control, and obviously the easiest way to deal with that would be to just have like a chiller or something, and then it's like you can just set the water temperature and it'll maintain it basically no matter what. But I don't have a chiller, so again, equipment limitations. Um, because any kind of water, like any radiator based water cooling loop, like ultimately you're restricted by ambient air temperature, right? So if ambient air temperature goes up 5 degrees, well, screw your test results. So yeah. And somebody's like, get AC. I don't have AC. And like, I'm not buying AC. So anyway, yeah, that's kind of the testing I did. I think it's kind of interesting. I'm kind of happy. Well, I'm not super happy with the data. It's just kind of like this is the best data I can produce for now. Hopefully, sometime in the future, I won't have like I'll have an oscilloscope that measures to 3 decimal points instead of just two. That alone would actually make a huge, like, that would be a major improvement. Um, but yeah, that's like the thing is just like I don't really want to buy another oscilloscope because they're really expensive. And these videos also don't get that many views. So it's just like the stuff that interests me the most is unfortunately the stuff that absolutely is not cost effective to produce. Anyway, yeah, that's it. That's it for the video. So thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. You can support me there directly. There's a link to it down in the description below. Maybe someday, if the Patreon gets big, big enough, I'll be able to buy a really nice high-end oscilloscope. Yeah. Man, freaking probes cost $1,000. Like nice active probes are literally over $1,000, which is just like, yeah, that's not great. Anyway, um, that's it.